So students, here we are going to discuss how to apply some of Newton's second law in some more cases with friction and uniform acceleration. When we have one mass or more than one mass, a system of masses that accelerate with the same magnitude. They're connected in some way and they both experience the same magnitude of acceleration. So we put together a lab for you, lab number 5, which deals with applying Newton's second law and uniform acceleration. And what we have in this lab is we have certain pre-lab problems set up that you'll look at, like Atwood machine, and then Atwood's machine on an incline. And we're going to look at how some of those equations of motion can be used in some of the simulations in this lab. So we have some pre-lab problems put together for you, some of which I'll discuss that go along with the simulations. So make sure that you do these pre-lab problems because they're those equations of motion and those free body diagrams that you do will play a big role in how you solve the lab parts. And the lab will be consisting of 2 main parts, the simulations 4 that we have, and a DIY do-it-yourself project which deals with making a ramp and sliding an object down the ramp at different angles to see at what angle you need to get it to slip and find the coefficient of static friction based on that. Okay, so let me go through some of these simulations. So to start off with our simulation, our first simulation, and this goes along also with the do-it-yourself element of the lab with the ramp. So what we have is a ramp with friction. And again, there's 2 different types of friction and notations used. So we have static friction, kinetic friction, or in some cases you could use capital Fs, capital Fk. Okay? So in this ramp with friction, what we have is we have our incline angle, and we have an object on it, a mass, and the idea is if this is stuck at a certain angle, we want to know how much do we need to increase our angle to slip. Okay. So we want to look at our variables to consider and understand the relationships between and relate would be your coefficient of static friction, see what role your coefficient of kinetic friction plays, or your force of static friction, your force of kinetic friction, see what role your mass plays, see what role your angle plays in this actual problem. Okay, so we want to see how all these variables relate to one another. So when we look at this, the most important idea is to put together a free body diagram and the equations of motion, and then we can put everything in perspective and see how these relationships hold. So if this object was moving down the incline, and let's say it had initial and a final velocity, which is in the simulation, which we could look at. We could also use kinematics to find some of those values. So if it was actually in motion, so here we're moving down, we're accelerating down the incline, which means by the second law we have a net force going down the incline because they're proportional to one another. What we know is we'll have the weight force, so Fg, the weight force acting on the mass, or a lot of times they use W for weight. We have the normal force perpendicular to the surface, okay? And then we also have kinetic friction. So if it's already accelerating down, then we know the friction will be kinetic and opposing the motion for which the object would take. So F, little f, Fk for kinetic friction. So those are all my different forces acting on the mass. And this will allow me to develop the equations of motion to see what roles these variables play. Okay, so as we know, we can break this down into two components. Because what we know is we have the weight force in two different components. So if this is my angle, I have my angle right here. And then this would be Fg in the y direction. This would be Fg in the x direction. So the components Fgx will be Fg, or your weight mg, your weight force, times, in this case, this would be sine theta. And then we have Fg y equals Fg times cosine theta. Okay. And this would be your free body diagram. And then your equations of motion. We would break down into two components. The sum of all my horizontal forces will equal the mass times the acceleration in the horizontal direction. And we know that the sum of all my vertical forces equals the mass times the acceleration in the vertical direction. So in this particular case, you could see that what's pesky here is the fact that we don't have a nice coordinate system aligned. We have to, based on the way I have my vectors set up, my force vectors, we have to find a convenient way of setting up my coordinate axis. So I'm going to align my x-axis parallel to the ramp plane. Okay, so that way I have, this is my x direction, all my force component vectors in the x direction. And then I'm going to align my y orientation with the normal force, so all my y component vectors will be aligned along this y direction, and it makes it easier to do the equations of motion that way. So the sum of all my horizontal forces, we know there's acceleration, so this is not equal to 0. In the case of kinetic friction, if we're solving for static friction, we will set this to 0 and find out what the maximum static friction force is, and we can extract our coefficient of static friction that way. In this case here, I'm going to say my weight along the x-axis is pulling it down, getting it to accelerate down, minus the friction force, the kinetic friction force, will equal max. Okay. And I'm going to give myself a little bit more room here. And what's going to happen here is we have mg minus mu k times the normal force equals ma. And I'll just say acceleration is only in the x direction. I'll drop my subscript. So here we have one equation of motion. We can plug in some knowns that we have and figure out our unknowns. And then from some of my y forces, we know vertically I have no net force here, so I should make my arrows look like they're equal and opposite to reflect that there's no acceleration along the defined y direction. So the sum of all my forces in the y direction must be 0. And what I have in this case is the normal force minus the vertical weight component of force must be 0. So my normal force is equal to mg. And, excuse me for a minute, this is horizontal is mg sine theta. Okay. And for vertically, this would be mg cosine theta. Okay, so remember that you do need to have your components here. I did forget to add that in here, but we made that adjustment. So my normal force here is mg cosine theta. So here I have a second equation. And I can plug, since I'm using Fn, and I can plug this value in I could substitute one equation into the other to help me solve for unknowns. I can use all the values I have. If I know the kinetic friction values, I could if I know the coefficient of kinetic friction, I could plug those in and the masses in, and I can find the acceleration value. And then you can use some kinematic equations too if you wanted to find out how fast, what the final velocity is at the bottom of the ramp. If you know how far it traveled and you know the acceleration from using your equations of motion, you could figure out what the final velocity is. And you could do some other, you could also figure out how long it takes to go down, etc. So there's a lot you can do with just finding the acceleration from these equations and then going on to solve other factors. Okay, so you're going to be playing around with this in both the pre-lab and the simulation. The next simulation that we have a little clip on for you is the Atwood's machine. The second simulation is Atwood's machine, which is a standard demo for uniform acceleration. So this demonstrates uniform acceleration. Hello students, here we are in our Questa physics lab. I'm here with Mark, and we got a Atwood's machine set up, which is what the standard apparatus setup we use for one of our physics labs. Okay, so explain to us what's going on with this Atwood's machine. What masses you have suspended on there?
Right now we have a 50-gram mass and a 50-gram mass connected by a string across a pulley. So since both of the masses are equal, it's not moving. If we put a 2-gram mass on one, then we'll have 52 and 50, and then we'll see what happens.
As your intuition would tell you, you would have more weight, so it should accelerate in the direction of the 52-gram mass. Is that what's happening? Are we seeing that? Yes. Here we have our smart pulley, and it's going to measure our timing. And there we have it set up. That's our 52-gram mass. And that is our 50-gram mass. Okay, so did you get a run on this, Mark?
Yes, I did.
Okay, so
well, I'll just show it again. But where you lace it, the 52 drops, 50 comes up.
Beautiful.
Then we have data on the screen. We can show data. We have position on the left. I'm going to auto scale it here. And you can see we have a parabola. That's our position data. And on the right here, we have linear speed. And this is our velocity, the change in velocity. We're going to fit the linear fit on that.
So the software program we're using is Capstone, and that's connected to the smart pulley. So the smart pulleys are taking our position time data from which we extract our velocity time data here. And with that information, we could find the acceleration of our Atwood's machine. So an Atwood's machine is an example of a uniform accelerated system, a uniformly accelerated system. So what we have is both masses are accelerating with the same magnitude, opposite direction. And a typical Atwood's machine is just like we see here, and as Mark demonstrated for us, we have the pulley in the middle and we have two masses on either end. And they will experience the same magnitude acceleration, but in different directions, depending on your case. So we have three cases where they were exactly the same mass, and as you may guess, they will not accelerate. The acceleration is 0 in that case. And then in case 2, if we have mass 1 greater than mass 2, which was illustrated by the 52 gram mass, you'll have acceleration in the direction of mass 2 and opposite for the other mass. And then on the other hand, if you exchange those and you make the mass 1 lower than mass 2, it'll accelerate in the opposite direction. So here is how you would look at the free body diagram for case 2, which we were just shown. And we got a sample of data, our position, time, velocity, time, information from our smart pulley. But if you wanted to find the acceleration in that case of 52 grams and 50 grams, you would do your free body diagrams, put together your equations of motion, and you would find your acceleration. You could find your theoretical acceleration using those values, and you could compare that to your data found on capstone via your smart pulley. So you have your position time graph, velocity time graph. From your velocity time graph, you would want to get your acceleration value. And did you get the acceleration value there, Mark?
Yes, that's the M. We have linear fetid, and we have an M.
Your slope is 0.166, so that should be your acceleration of the system for these two masses in which we were shown here. All right, thank you, Mark. Wonderful setup. Okay. Okay. And a simple Atwood's machine is just we have a pulley and we have two masses suspended vertically. Through that pulley via string or a cord, so there's tension. Okay, so we have two masses connected via string or cord through this pulley. And depending upon the ratio of the masses and the value of the masses, we would see either no acceleration or acceleration towards mass 1 or acceleration towards mass 2. So this all depends upon what these mass values are. So we have three cases for our acceleration, our uniform acceleration. Number one is if mass 1 equals mass 2, you could intuitively see that the acceleration is going to be 0. We should get no motion, right, on this Atwood's machine. And in the second case, if M1 is greater than M2, then we have acceleration of mass 1 going down. Okay, so the acceleration will be down in M1's direction. Okay, and the third case is the mass of 1 is less than the mass of 2, then we're going to have acceleration that is upwards for M1. Because what's going to happen is M2 is going to pull, it's going to communicate its force via the tension of the string, which will pull M1 up. So there's this connected force here, right? Okay, so now we have this nice relationship that you could verify in your equations and for Atwood's machine, and that is the acceleration is we have acceleration is equal to some constant times g, depending upon what the ratio is, okay? And that is going to depend upon your mass value. So we could derive this, which for me is easier to do than just from trying to memorize the formula. But here's a formula that we get. You may have seen this. You'll probably see this in some standard textbook. The acceleration of either one of these masses. So again, we have to analyze this problem, we have to look at each mass individually, do a free body diagram for each, do the equations of motion for each, and look at the relationship between those two. When you do that, you can look at the acceleration of each mass based on this. Okay, so it's a ratio of g. So how do we get this? Well, to get from the three cases. Okay. So for the first one, M4, let me go ahead and look at the first case. Erase this. Oh, not the first case. The second case. Because the first case, if these two are equal, if M1 and M2 are equal, you could see that this is going to cancel out. You'll get 0, and your acceleration is 0 times little g, which is 0, and there's no acceleration as we predicted. So let's go on to the second case to get this. Or for the case M1 is greater than M2, let's go ahead and do a free body diagram. For M1, our free body diagram would be, okay, if we think about our Atlas machine, M1, if it's heavier than M2, it'll accelerate in this direction, so this would be Fg for 1. Okay. And then tension on 1, we'll pull it upward. There's a tension force, and I'm going to use, I'm trying to get out of the habit of using W's and T's. I'm going to call this Ft of 1. Okay, and we know that it's going to accelerate this direction because that's the direction of your net force. Okay, for M2, we know that we're going to have, it's going to be pulled upward, right? This is 1, this is 2. We'll have less weight because it has less mass, Fg2. But something curious we know is going to occur, which is that these tension forces for each should be the same. So what we have to note here is 2 important relationships. Okay, so we could say the tension Ft is equal to, Ft1 is equal to Ft of 2, which we're just going to say is Ft. The tension, the magnitude of tension more specifically, because the directions could differ, but the magnitude of the tension is the same. Now also what we have is, in the same sense, we also note that the acceleration of 1 is equal to the acceleration of 2, which we'll just say is the acceleration. So the accelerations are equal in magnitude as well. Okay. And this one's going to have accelerate. So in this case, this tension force is more than the weight force. So this one's going to accelerate upward, and that's where the net force is. There's a net force pulling it upward. So here we have our free body diagrams. Next thing is to do our equations of motion. And I'm going to start with M1. And the way I do these is I look at the directions and use my sign convention of up positive, down negative, and incorporate those into my equations of motion. Okay, so because we know forces are vectors, accelerations are vectors, so we have to count those in. So if I look at M1, the sum of all my forces on 1, vertical forces on 1 is equal to the mass 1, the acceleration of 1 in the vertical direction. Okay, so we know this is non-zero because it's accelerating downward. So what I'm going to do is the positive is up, so I'm going to say the force of tension on 1 minus, this is downward, so it's a negative vector, the weight force on 1 down will equal the mass of 1 times the acceleration, which will be negative AY1. So now rewriting these and noting these equivalences, I'm going to clean this up a little bit. I'm going to say the force of tension, because these tension forces are equal in magnitude, is equal to, I'm going to bring this over, and this is M1G, and this is going to be a negative minus M1 times A. Okay, because again, remember it's accelerating downward. So here I have one equation of motion, label as 1. Now when I look at the equation of motion for the second mass, which will allow me to do the problem solving, M2 In this case, I'll say the sum of all my forces in the vertical direction for number 2 will equal the mass of 2 times the acceleration in the y direction of number 2. And what I get in this case is I have acceleration upward and it's being pulled upward. So we have the force of tension of 2 minus F, the weight force on 2, will equal positive M2AY2. Okay, and cleaning this up a little bit, we'll say the force of tension will equal M2 times G plus M2A. Okay, so I have these two, the second equation. So I have 2 equations, and if you knew the tension, you could solve for acceleration. If you knew the acceleration, you could solve for tension. But what you have is a system of equations. So what you could do in this case is you could set these two equal to each other and solve for A, and you get this equation right up here. You get this relationship. So what you want to do is you set sub and solve for your acceleration, okay? And you could get that value. And you see this nice clear-cut relationship. And then you could get your acceleration in terms of little g. And the Atwood machine is really interesting in that you measure acceleration, uniform acceleration, and that value is going to depend upon your little g value, your acceleration due to gravity. So an Atwood machine can be created somewhere where you don't know your local g value. You can solve for this. So if you measure an acceleration, you could find out what your local acceleration due to gravity value is. So if you're on Mars and you wanted to figure out this 3 to 4 meters per second squared value of acceleration due to gravity, you would construct this, measure the acceleration in your experiment, and you could find this little value based on your masses as well. So it's a neat little trick. So you could do the same thing when mass 1 is less than mass 2. The only difference will be the size of the vectors there. As your signs in your equations will change. Now the third simulation is just Newton's law with photo gates. I'm gonna give myself a little more room here. And this is based on some of the same principles in your pre-lab problem. The third simulation, it's 2 masses connected, but now in the case of the Atwood machine, we have vertical and vertical forces. Here in this simulation, we're looking at Newton's laws with one that's set up horizontally and one that's connected vertically. And we're also looking at our position, velocity, acceleration relationship. So we're going to be jumping back and forth from using our dynamics and our equations of motion and then connecting that with kinematics that we did before. Okay, so we have, in this case, we have this frictionless surface, and we have these photo gates, and we have this object, this mass that's connected via tension through a cord to another hanging mass here. Okay. And I don't think they gave you any labels, but it's always important to distinguish between your 2 masses. So I would call this like mass A. We call that mass A. We call this mass B. Okay. And depending upon the ratio of the masses, you're going to see some acceleration. So how A is going to move, accelerate, will depend upon the surface, whether there's friction or not. So if it's frictionless, it's going to be able to be pulled with a lot less mass than if there is friction. And then B's mass ratio will help determine that as well. So the idea is it's going to tie these photo gates in this experiment. This is going to time, so this will give you a time. This will give you position, velocity, and time info. And what we could do is time this and we compare to the acceleration from the second law, applying our equations of motion. Okay. So what we want to look at is how to set this up. So again, what you want to do is there's two setups. So you're going to look at your free body diagram for mass A. And in that case, you're going to have force of gravity on A acting down, a normal force acting up, because there'll be no acceleration up and down. The only acceleration you're going to have is it's going to get pulled. You'll say this is the force of tension on A. So you're going to have a net force in that direction, acceleration in that direction. So you have the sum of your vertical forces equal MAY, which equals 0. And you'll have Fn equals mg, okay, mass of A, and then the sum of all your horizontal forces equals max, and that's going to be non-zero, and this will be FTA, the force of tension will just equal your mass times your acceleration. If you had friction, you would add that on there. Okay. And that's your second equation. So I'll just say force of tension, because what we're going to see here again is that the tension pulling on A will be equal in magnitude to the tension pulling on B. Okay. And then the free body diagram, and these are our equations for MB will be like we did in Atlas. We're just going to have, if it's accelerating, and I'm basing this on acceleration downward. So in my picture, I'm saying acceleration is this way, and acceleration this way. So I'm stating that there is acceleration by my free body diagrams, and setting it up so that we could find that unknown acceleration. So in this case for B, we have acceleration downward, so this would be Fg on B, excuse me, and then we should have a smaller tension force here, smaller than the weight of B here, so Ft on B. So in this case, we have acceleration down, and my equation, here I only have one equation. I have no horizontal pieces here, and it's the sum of all my vertical forces equals mass of B times the acceleration in the vertical direction of B. In this case, we're going to have tension of B, which equals a tension of A, so I'm just going to say Ft minus Fg on B will equal MBAY. Okay, so I could clean this up a little bit more. I could say the tension force will equal M of B, the mass of B, times little g plus the mass of B times A. And the acceleration here is downward, so I need to put in my negative here. So I'm going to say minus MBA. So you got to be very careful with your signs. So here my convention is positive to the right and positive upward. Okay. So I'm going to use those conventions inside my equations. I insert them with the signs. Very careful. Be very careful when you do that. And this acceleration, I'm just going to say is the same, because what we note here is that the same conclusion, that Ft on A equals Ft on B, that the tension force is equal in magnitude for both of them, and also the acceleration is equal magnitude for both of them, even though they're in different directions. The magnitude's the same. Okay, this is what we mean by uniform acceleration. Very important detail. So just double check your signs and your subscripts. It's very easy to mess up on those, but you could see that you could solve for your acceleration by substituting. And I should put my subscript here too. Okay, that way I distinguish between MA and MB, so I could set these equal to each other. I could solve for my acceleration, and you could find a lot of different unknowns this way as well. Now the next simulation is a little twist on Atwood's machine. This fourth simulation is an incline Atwood's machine, which makes it a little interesting. It's basically what we just did, but now let's add some angles into the mix, right? So this fourth simulation is an inclined Atwood's machine. And the idea is, okay, what's going to happen when we start adding an angle into the mix, right? So we went from this flat surface, but let's say we go ahead and add an angle in here. All right, let's make things a little more difficult. Let's get a mass here accelerating up an incline by connecting it to another mass that's suspended. Okay. So now we're going to have a mixture of horizontal and vertical components by doing that. So here we have a few more adjustments to make. And let's go ahead and add friction, right? So we're going to add some friction with this. And if we knew the masses and some other aspects, we could solve for coefficients of friction. And the way I have this set up, I'm going to label it the same way I have it. I have M1 and M2. So here I have this labeled as M1, careful, and this is M2. And we want to know is M1, M2 ratio to accelerate. Okay. Like what ratio of masses do we need to actually pull M2 up the incline? Maybe M2's ratio with M1 is such that it actually goes down instead, right? What's the balance here? And how is this the angle to accelerate up or down as well? So what happens to our angle? What angle do we need to actually get it to accelerate down this way or up the incline? So there's a few things that we want to consider and think about. And how does friction play a role? And what is the coefficient or the role of, this is K comma S, the role of the coefficients of kinetic and static friction in the problem? Okay? And at what point are they stuck and static based on the friction values? So the most important thing here is the setup that you're going to do. So when you look at this, again, you have to do a free body diagram, let's say of M2, and we're going to do this carefully. So we'll see that this is again going to depend upon this angle, and that we're going to have weight acting down, and we'll have the normal force of 2 acting upward, and we're going to have tension, so we're going to have Ft on 2 pulling it up, and we really don't know the ratio of masses yet. So if I assume that it's accelerating in this case, and I don't plug in for my mass, then I'm going to show that my tension vector is more than my weight. So I'm going to have two things here. I'm going to have a little bit of friction. It's accelerating, so it will be kinetic friction in this direction. But here I'm also going to have some x component of weight. down. So weight will be, this will be mg, here's my angle. This will be mg sine theta, just as before with the ramp, and this will be mg cosine theta. So just remember how these work. So if I were to do the equations, so that's my free body diagram. If I cleaned it up a little bit, it's really just based on my convention I used before, x that way, y that way. So I have normal, Fn, Fg, Ft, and then Fk, kinetic friction. Okay. So my equations are going to be somewhat a little more intricate for this one. The equations will be the sum of all my forces along the horizontal direction defined by my convention here will equal mass times acceleration, mass of 2, acceleration of 2 in the x direction. Okay, and that's going to be non-zero by the way I defined it here. For this situation, again, you have to adjust for each one. So what we have is we have the tension force of 2 minus the weight of 2, the x component weight, okay, of number 2. And then what we're going to have is minus also any friction, kinetic friction force of 2 will equal m2a. And what we know is, again, the a's are equal, right? So a1 equals a2, which equals a. And this one is along the x direction, that one will be along the y direction. So the magnitudes are equal again. So I could drop that. The same with the tension. So T, we know that Ft1 equals Ft2, which equals Ft. So what I have here is my equation breaks down to Ft minus m2g, and it's the component, x component, so it's sine theta, okay, minus uk times the normal force Fn of number 2. That's not going to be the same as number 1. That one we have to leave in, equals m2 times a. You got one huge equation here. Okay. And this is for m2, so the equations for my y forces on number 2. Now this is 0 because there's no acceleration in the y direction, so this one's going to be a lot easier to do. So this will be, what we have is Fn2 minus the gravitational force on 2, but the y component equals 0. So Fn2 will equal mg cosine theta. And that's m2g cosine theta, what we lined up over here. So here we have another equation. We can plug this into this value right here, and we have a lot of relationships between our variables, right? So we can understand more of the dynamics of changing one variable and what that does to the other. The next step here would be to look at our free body diagram of M1, and we're going to come up with one more equation that will allow us to solve for unknown. So if it's accelerating in the direction I said, it's accelerating up the incline, accelerating down the incline, then what we can do here is connect all our equations together. So for M1 here, we're going to have FG1 is going to be much more than just the tension force on one. Okay, so my equations will be just in the vertical direction. So here we have the sum of all my vertical forces equals MAY, and that's for number 1. And in this case, that's non-zero. So I have the tension of 1, which I'll just say is Ft, minus the weight of 1 will equal the mass of 1 times the acceleration that 1 undergoes, which will be negative because it's going downward. This is my negative direction. Okay, so here we have negative down, positive up. So this will be negative AY. So cleaning this up in one more step, we'll say the tension force acting on mass 1 will equal M1G, that's just straight vertical weight force, plus or minus M1 times A. So here I have another equation. Okay. And again, these are equal, as we know from before. The accelerations are equal because it's uniform acceleration. And the only thing you have to watch out for is the normal force for 2. Well, that is only with respect to mass 2. We don't have a normal force in this case. But what we could do is we could solve for our angle based on different mass values, and if we know our coefficients of friction. So we could use these 3 equations. We could do a lot of substitutions, plugging in values to solve for unknowns. And then the other thing is to note that if we have our acceleration value, and let's say we wanted to know how far this will go down, and we know it's accelerating downward. What's this height right here? Well, you could use your kinematics. And then you could know that, you have an initial velocity and the final velocity, you have an acceleration, and you could find out how far it would actually displace from its initial position. So you could use some kinematics based on what you solve here to solve a little further, solve for other unknowns, connect it with your kinematics. Okay. And so those were your simulations, and just last note for your do-it-yourself. DIY project, and you're just looking at angles to slip, and you want to note that your coefficients, different coefficients of static friction affect the angle. Okay, we want to look at building a little ramp right here. So we have our angle, and we have some mass on that ramp that we build. Okay, and what happens as we increase that angle? If it's stuck right now, right? So it's stuck. So we know that the weight is being counteracted by the friction force, right? Fs. We have maximum static friction. We have static friction until it's maximum, and that is going to be opposing the weight Fgx component. Okay, so we want to get this unstuck. We want to keep raising this angle until we get it to slip, and we want to measure those angles to slip. So we measure and take an average. Do it 2 or 3 times so you get an average value. And then if we try a different surface, or if let's say this is a box that we have, maybe a box of jelly we're trying, let's try a different orientation. So if we have it flat on the surface, if we change it to being on its side, will that affect the angle that it slips? And no, it should not, because it's going to be, it doesn't matter how you do the contact surface, you're still going to get the same value. Okay, it should still slip. It still has the same interactions between the surfaces. Doesn't matter what areas you're putting together there. So any side that you do will give you that same effect for slipping. So the other thing, what we want to do is we try to add a stickier surface. And then what happens to our μs value? μs, what happens to our angle? Okay, what happens if we put like sandpaper underneath this? Well, what we'll notice is that we'll have to tilt it and increase the angle significantly to finally get it to slip. And then you could time the whole thing, you know, and you can measure your position from the top, that where you release your mass, to the bottom. You could time it, and then you could also use that to find the acceleration. If you time it and you have an initial and a final velocity, you could find your acceleration that way as well. So anyway, so there's a few variables, but mostly we want to look at being able to compute your coefficient of static friction and your angle value. And if you notice, your coefficient of static friction, based on what you did on your pre-lab, you just get the tan theta value. So your US is just tan inverse of theta. So you want to be able to look at this particular relationship and explain that. All right, that's it. So probably above and beyond the details you need, just make sure that you work through all this. All right, thanks, bye. Okay, now the moment I start raising this and creating an angle of my incline, which would be right here, okay, and I could measure the angle using a protractor. So the moment I start raising this, I'm going to create my weight force so that it's going to act in two different directions, two different components of motion. So what happens is now I have my normal force acting perpendicular to the surface this way, but my weight is going straight down to the center. So it's going to have, I'm going to have a vertical component of weight acting down, and I'm going to create this horizontal component of weight that will eventually at a certain angle create to accelerate down the ramp, because it'll create a net force in that direction. Okay, so as I lift this up, okay, you notice it's not moving yet, and that's because it's stuck. There's static friction holding this up. So right now I have some weight force horizontally, but I have a static friction force. It's a contact force between surfaces. So that's holding it and opposing that weight force. Up until the point I get to a certain angle and it accelerates down the ramp. At that point, the static friction force is the kinetic friction force, and it opposes a weight force, but it's going to be a lot less, whereas the X component of weight force has a net force going down the ramp. Okay, and that's my horizontal axis. And still I would have my upward normal force counteracted by my Y component of weight. Okay, so I'm going to try here. Can you repeat this? So it's really important to analyze all the forces, look at the angles, and make sure all your vectors sum up along the horizontal direction and the vertical direction. Get your equations of motions correct. So at some point, this accelerates down. Okay? So again, we have friction, kinetic friction, X component of weight, normal up, and Y component of weight down. Now, to add a little bit of a challenge to this, I'll have dog assistant here. We're going to create a little more stickiness. So we're going to create a little more static friction between our surface of the wood and the ramp. And as you can, yes, this will create a situation where we'll need a steeper angle to accelerate the block down the ramp. So I'm going to lift. And you can see it's going to take a lot more angle to get that weight component of force along the horizontal axis to get it to overcome the static friction force and have a net force equivalent to the mass acceleration in that direction. Here we go. Voila, there we go.